let's compute the value of another series. A bit of algebra will make a huge difference here. 1 divided by k plus 1 times k is the same as 1 over k minus 1 over k plus 1. See why this is true, right? I can write these over a common denominator of k plus 1 times k. That means that 1 over k is k plus 1 over k plus 1 times k. And 1 over k plus 1 is k over k plus 1 times k. So now I've got k plus 1 minus k in the numerator, and that's just 1. Why is that helpful? It'll take us a little while to see how that algebra fact helps. But in the meantime, remember what our goal is. Our goal is to evaluate this series. And instead of just diving straight into that, let's evaluate a slightly simpler sum. Instead of k goes from 1 to infinity, let's just do k goes from 1 to 5 of the same thing. Of course, this is small enough that we can just do the calculation. So to calculate this, I just plug in k equals 1, k equals 2, k equals 3, k equals 4, k equals 5 into this expression and add it all up. Let's see. I plug in k equals 1, and I get 1 over 2 times 1. And I'll add that to what I get when I plug in k equals 2, which is 1 over 3 times 2. And I'll add that to k equals 3 term, which is 1 over 4 times 3. And I'll add that to the k equals 4 term, which is 1 over 5 times 4. And I'll add that to the k equals 5 term, which is 1 over 6 times 5. So all I've got to do is just do this arithmetic. And I can simplify this a bit. Instead of writing 1 over 2 times 1, I'll just write a half. Here I've got 1 over 3 times 2 is a sixth. Here I've got 1 over 4 times 3, that's a 12th. Here I've got 1 over 5 times 4, that's 20th. Here I've got 1 over 6 times 5, that's a 30th. And all I've got to do is add up these fractions, which I can do. I put them over a common denominator of 60. Here we go. 1 half in 60ths is 30 60ths. 1 sixth in 60ths is 10 60ths. Over a common denominator of 60, this becomes 5 60ths. Common denominator of 60, this becomes 3 60ths. Common denominator of 60, this becomes 2 60ths. And just add up the numerators. 30 plus 10 is 40, plus 5 is 45, plus 3 is 48, plus 2 is 50. So this entire thing is just 50 60ths. But instead of writing 50 60ths, I could just write 5 sixths. Alternatively, we can make use of the algebra fact from the beginning. What was that algebra fact? It was a fact that 1 over k plus 1 times k is the same as 1 over k minus 1 over k plus 1. Now, why is that helpful? Well, that means instead of writing down 1 over k plus 1 times k, I can write down this. So when k equals 1, instead of writing down this, I'd write down this, 1 over 1 minus 1 over 2. And when k equals 2, instead of writing down this, I'd write down this, 1 half minus a third. And when k equals 3, instead of writing down 1 over 4 times 3, I'd write down this, a third minus a fourth. And when k equals 4, instead of writing down this, 1 over k plus 1 times k, I'm going to write down a fourth minus a fifth. And the last term, the k equals 5 term, instead of 1 over 6 times 5, it'll be 1 over 5 minus 1 over 6. Why is this an improvement? Well, the cool thing that happens here is that most of these terms end up canceling. Take a look. I've got a minus 1 half plus 1 half, minus a third plus a third, minus a fourth plus a fourth, minus a fifth plus a fifth. The only terms that survive here are this initial 1 over 1 term and this last minus 1 over 6 term. And that means this entire thing ends up just being equal to 1 over 1 minus 1 over 6, which is 5 sixths. This trick has a name. We say that the series telescopes, and we'll call such a thing a telescoping series. What about the original series with infinitely many terms? This is the original series that I want to compute the value of, and this is by definition equal to the limit as n approaches infinity of the sum k goes from 1 to n of 1 over k plus 1 times k. We can compute this limit. Well, this limit is the limit as n approaches infinity of the sum k goes from 1 to n. And instead of writing this, I'll write 1 over k minus 1 over k plus 1. And this will be a much better way to write it, right? Because what is this? This is then the limit as n approaches infinity of, what we write down the first term, it's 1 over 1 minus 1 over 2, plus the next term, the k equals 2 term, which is plus 1/2 minus 1/3, and I'll write dot, 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 plus the last term, which is 1 over n minus 1 over n plus 1. That's when k equals n. But practically all of these terms die. This minus 1/2 is killed by this 1/2. This minus 1/3 is killed by something. Every single term here. There's a term in here which kills this 1 over n. The only thing that's left is this initial 1 over 1 and this final minus 1 over n plus 1. So this limit is just the limit as n goes to infinity of 1 over 1 minus 1 over n plus 1. But what is that limit? Well, this is 1 minus 1 over an enormous number, right? So this limit is just 1.
Let's formulate this as a general trick.
Suppose that I want to take a sum, k goes from 1 to n, of some function evaluated at k minus the same function evaluated at k plus 1. Then this is what? Well, it's f of 1 minus f of 2. Plus f of 2 minus f of 3, and so on until finally I get to the last term when k equals n. It's f of n minus f of n plus 1. And just like before, practically all the terms cancel. This f of 2 and this f of 2 cancel. This minus f of 3 cancels something. And the previous term here cancels this f of n. So this sum is equal to f of 1 minus f of n plus 1.
And taking a limit lets us say something about the infinite series.
So now suppose I want to calculate the sum k goes from 1 to infinity of f of k minus f of k plus 1. Well, this infinite series is by definition just the limit as n approaches infinity of the sum k goes from 1 to n of f of k minus f of k plus 1. But I just saw how to calculate this. This is now the limit as n approaches infinity of, well, what's this? This is f of 1 minus f of n plus 1. But this is now a limit of a difference, and the limit of this first term is the limit of a constant, which is f of 1. So this is equal to f of 1 minus the limit as n approaches infinity of the function f.
Let's do another example.
This fact again. Let's try it. Let's try to evaluate the sum k goes from 1 to infinity of k over k plus 1 factorial. And the trick is to rewrite this as a telescoping sum. So I got to cook up some function. And the function I'm going to use will be the function f of k is 1 over k factorial. And I just want to check that f of k minus f of k plus 1, well, what is that? That's 1 over k factorial minus 1 over k plus 1 factorial. But writing this in a common denominator of k plus 1 factorial, this is k plus 1 over k plus 1 factorial minus 1 over k plus 1 factorial. And what happens here is that I've got a k plus 1 factorial in the denominator and a k plus 1 minus 1 in the numerator. That's a k. So indeed, this sum is the sum k goes from 1 to infinity of this function, 1 over k factorial minus this function at k plus 1, which is 1 over k plus 1 factorial. But now this infinite series is just its value of this function when k equals 1, which is 1 over 1 factorial, minus the limit as n approaches infinity of this function. All right, 1 over n plus 1 factorial. But this limit is 0. And that means that this infinite series has value 1. And